mainly from L2 of 0, 1, right? Function spaces and the inner products in function spaces. So mainly topics involving L2 of 0, 1, capital L2, right? Function spaces. So Fourier series is already introduced, right, through projections, right? So you project a function x of t on sinusoidal functions, and the resulting thing you get is the Fourier series, right? You have been introduced to this part. So let us see more about this Fourier series today. So let us consider a real signal x of t. Okay. So a real signal x of t, okay, and you are considering the t varying in 0, 1. Okay. So now what is this xk of t? Xk of t given with this sinusoidal form. Sinusoidal form is involving cos and sine, right? So here you are having this kind of an expression where a naught, a1, ak, each of this expression are given in terms of the inner product. So if you have a signal x of t, then a naught is inner product x comma 1. So you are using the inner, here you are referring to the inner product in L2 of 0 comma 1. That is why for this inner product you are doing 0 to 1 x of t dt, right? And AL is 2 times of inner product x comma cos 2 pi lt, okay, for AL. So for 1 means it is just 2 pi t, which is 2 times of integral 0 to 1 x of t cos 2 pi lt dt. Same way for BL, instead of cos you just have sine. Okay, so this is your xk. And what we have seen about this xk, so in this interval 0 comma 1, xk of t approaches to this signal x of t, maybe except for a few points. Okay, so if you have this xk of t given by these coefficients, then it will converge to x of t. So what was the example given? So the example is that if you are taking, say, the very simple function x of t is equal to t. Okay, just look at the graphs of x1 of t. So this one is x1 of t, so here this is x4 of t, right? So as you increase the k value, you can see that the curves are going closer and closer to this line x of t equal to t. And when you say, for example, k is equal to 128, you see the values are very much close to this x of t equal to t. Okay, so only at the end points they are not coming closer, but otherwise you can see they are going very closer to this line x of t equal to t. Okay, so here you see that xk of t approaches this x of t, okay, as k tends to infinity. Okay, fine. So now this is the Fourier series in the interval 0 comma 1. Now how to do the same Fourier series in the interval 0 to t? In the 0 to t, what happens to norm? First of all, here in 0 to 1, you see that here norm 1 means it is integral 0 to 1, but here what is norm 1? Here also we are looking at a real signal only. Okay, here also we are looking at a real signal, but what is the norm 1 in L to 0 comma t? Here it is integral 0 to t modulus of 1 square dt and the whole power 1 by 2, right? So now you see that this integral 0 to t, this is just 1, and then when you apply the limits you get t minus 0, so just t power 1 by 2, which is square root of t. So is this clear that why norm 1 squared is equal to t? At the first sight you may feel that it is very strange that how can norm 1 squared be t? But when you are looking at this particular norm, that L2 of 0 comma t, then when you do the integration you see that the norm is t. Is it clear why norm 1 square is t? Yeah, yes or no? Only if there is a response I can continue. How many of you understand? Give a thumbs up at least. Why norm 1 squared is t? Is that part clear? What about others? Okay, at least two of you are responding. Good. Okay, so the next thing here given is that cos 2 pi l t by capital T, the norm of this is square root of t by 2. How is that? So exactly same method. So 0 to t modulus of cos 2 pi l t by t whole square, right? dt. Now what is this? So it is just cos square 2 pi l t by t. Now applying this formula here, you can rewrite this as 1 plus cos 4 pi lt by t whole divided by 2. Okay. Now 1 by root 2. So you, what is that? This one, just this denominator 2 alone you are bringing out of the integral. So 1 by root 2 I have brought out, and then I have splitted the integral, right? And then you see that the first part is 1 by root 2 and the second part becomes 0. Why? You see that this cosine is a periodic function of period t, right? So here you see that when you take 4 pi l t by capital T, so when you complete this 0 to t, you will have completed two circles, right? So you see that the area will cancel out and become 0, right? So you see that integral 0 to t cos 4 pi l t by t dt is 0. Okay, and then you have t power 1 by 2, so square root of t by square root of 2, so it is square root of t by 2. Okay, so just we have did the integration here and found the norm of this. So norm square will be just t by 2, that is what is given here. And the exact same procedure for sine as well, right? You apply the formula, you split them, and then you see that this part is now 0, and then you see that the remaining gives you square root of t by 2. Okay, fine. So here you have 1 plus cos and here you have 1 minus cos. That's all is the difference. Okay, so in both the cases you are getting the value to be t by 2. So all the norms, how we got the norms we have seen. So the next part is that now we have to project x of t onto this. How did we get this? See, we started with 1 cos 2 pi l t by t and sin t l pi t, sin 2 pi l t by t. Now you see that how to normalize a given vector. Suppose you have any vector. Suppose you are having any vector v. How do you normalize the vector? Can anyone tell? How do you normalize the vector? How can you make the vector to have norm 1?
Vector divided by the norm.
Divide by the norm, right? Exactly, that is what we are doing here. Okay, so here what we are having here is nothing but vectors, right? And they are orthogonal vectors. Now we are trying to make it as norm 1 vectors. So we are finding the norms and then dividing each of the vectors by its norm. So when you divide by square root of t by 2, you will get square root of 2 by t in the numerator. Same way here square root of t I have divided. So every term we are dividing like this. So this is what you have got. Okay. So now you see that applying the projection formula, you will get this term. Okay, so inner product of x comma 1 by root 2 root t into 1 by root t, and inner product of x comma square root of 2 by t cos 2 pi t by t, and so on, like this. Okay, so this is the projection of x of t onto this particular space, and this for this particular space you can see that this is an orthonormal basis. So for orthonormal basis, what are the things you need? The inner product should be 0 for any two terms, right? Any two distinct terms, the inner product is 0 and each of them should have norm 1, right? And using this kind of a formula, you can easily check that the inner product is 0 for different vectors, and for the same vector, you can see that the norm is 1. Okay, because we have divided by the norms here, so now each of them have norm 1. Here it is just an orthogonal set, 1 cos 2 pi l t by t sin 2 pi l t by t. They are just orthogonal, we made it as orthonormal. Okay, so for projecting, this is what we need. We need an orthonormal basis, and we have done the projection. Okay, so now what are we doing? So here you have a 1 by root t and 1 by root t, which becomes 1 by t, right? So this is now 1 by t inner product of x comma 1, which is 1 by t integral 0 to t x of t dt. Okay, so what is that we have done? So 1 by root t into 1 by root t is 1 by t inner product of x comma 1, and this is your a naught. Okay, so your a naught is 1 by t inner product x comma 1 is nothing but integral 0 to t x of t dt. Okay, and here what is that you are having? Here you are having a square root of t 2 by t, and here a square root of 2 by t is there. So when you combine, multiply these two, you will get 2 by t, right? So that 2 by t has come out here, and then what is that remaining? So for example, here let's write a1 is 2 by t inner product of x comma cos 2 pi t by t. Okay, and then you have this term cos 2 pi t by t, which is here. So now what is this inner product? This inner product is nothing but integral 0 to t x of t cos 2 pi t by t. Okay, so this is the first term here. Okay, so same way you have the second, a2, a3, everything is given. For L is equal to 1 to k, and same way you have BL. For BL you have sine terms. Okay, for BL you have sine terms, and for AL you have the cos terms. Okay, so you see that by projecting x of t onto this orthonormal basis, we have got an expression for xk of t. Okay, so it is almost similar to what we have obtained here, right? So instead of 0 to 1, now we are having 0 to capital T, and instead of 2 we are having 2 by t, right? So that is all is the difference, and otherwise everything is similar, right? Okay, so now we have got the expression for the Fourier series in which interval? In 0 to t. Okay, now what is the length of this interval? What is the length of this interval 0 to t?
T.
T. Okay. Now what about the length of this interval minus t by 2 comma t by 2? So you are having the real line, and this is your origin, and here you are having t by 2, and here you are having minus t by 2. So now what is the length of this interval?
T.
Again t, right? So now we are just looking at any length of t, any interval of length t. So it is a same expression. Here you are having a 1 by t, and instead of 0 to t you are having minus t by 2 t by 2. Okay, in fact, instead of this interval or 0 to t, or you can replace it with any interval of length t. Okay, so maybe t to 2t. Okay, so any interval of length t, you can have a similar formula. Okay, fine. So we have seen the Fourier series formula for any interval for 0 to 1 and then 0 to t, or any interval of length t, in fact. Okay, so now here, how can we periodically extend this signal? What is mean by periodically extending? So here you see that you are having this x of t is equal to, it is very much like x of t equal to t, right? Okay, so let us consider that function. For example, here suppose you are having that function for minus t by 2 to t by 2. Okay, and then you are going to repeat the same. Okay, you are just shifting and getting the same in the next interval of length t, and again in the next interval of length t. Okay, the same graph you are going to repeat every time. Okay, so it means what? We have just periodically extended. Here the period is t, so every time the graph repeats over a period of t. Okay, so here the period is t, and the frequency is 1 by t. It means what? Within an interval of length t, you are having the cycle only once. Okay, and the nth harmonic means n by t. It means what? Within intervals of within n times of t, you will have n functions repeating the same, right? So you can see it better in this case. For example, if you look at this function here, so this cos function between 0 to 1, here when the frequency is just 1, you see that it is repeating only once. But when the frequency increases, here you see the same curve within 0 to 1, the period is exactly the same, but the frequency has increased. Here the frequency now it is 3, so you see that the frequency it is repeating thrice, once, twice and thrice, and here you can see it 4 times. And the same, this is for cos, and here you are having the same for sine. Okay, so you see that as the frequency increases, more number of cycles occur within the same period. Okay, fine. So here, now we have seen within 0 to 1 or within a interval of length t how to find the Fourier series. That is what we have seen here. Now how to extend it for periodic signal. Okay, so for periodic signal also it is very much simple. You have to just integrate over p, where p is any interval of length t. Okay, so the formula is exactly the same. Okay, so you take a real signal x of t, periodically repeated to get xp of t. Okay, so here you see that now you take any interval of length t, you integrate, you will get the Fourier series. Okay, so what have we seen so far? What is the Fourier series for 0 to 1, 0 to t, minus t by 2 to t by 2, and then we periodically extended the function first of all, and then we saw what is the Fourier series for this periodic signal as well. Okay, fine. So here is an example of the periodic function. Here you see that, so you are having a periodic function. Okay, x of t is equal to t is repeated over. What is the period here? Can you see? What is the length? You see it starts from here to here. What is the length? It's
2 pi.
2 pi, right? So over every 2 pi it is repeating. Okay, now when the frequency is increased, you see what's happening, right? So you see it's, you have 2 bends here. Now when it is increased further, you have 3 bends here, even increased. Okay, so when k is equal to 1 2 5, you see how this is converging towards this line, right? So you see how this xk is converging towards this line. Okay, so as the k value keeps increasing, what happens, this will converge to this periodic function, right? So now you can look at the complex exponential form of Fourier series. So for complex exponential form, here what is that you are having? Now you are having a complex signal. Earlier, whatever we have seen, we had only a real signal. Now we are having a complex signal. Okay. So for complex signal, what is the function here? We earlier we saw that we have taken 1 cos omega t and sin omega t, right? And here we are now going to consider e power I omega t. Okay, so here this omega I am referring to this 2 pi l by t, all these things. Okay, so here you see that we are considering norm of e power j 2 pi lt by t. Now what is this e power j 2 pi lt by t? So we can compute the norm. What is the norm in the complex space? Do you remember? What is inner product of x comma y when x comma y are in the complex, the codomain is in the complex field? How do
X,
you
Y.
define integral? Let us say in 0 1, here maybe 0 to t, it is integral 0 to t x of t, and for y of t you have a conjugate, right? Dt, right? This is how we define. Okay, so now here first of all for norm, you simply have the square, right? And what happens to mod e power I theta square? What is this? Modulus of this square is, what is this? The modulus of this is square root of cos squared theta plus, sorry, cos squared theta plus sin squared theta, right? So it becomes 0, sorry, 1, right? So cos squared theta plus sin squared theta, you know that it is 1, and that's why this becomes 1 here, right? And then you will have here the integral. When you apply the limits, it's t and then power 1 by 2, so it's square root of c. So that norm is t, norm is square root of t, and the norm square is t. Okay, and this is true for any integer l. Okay, this is true for any integer l. Okay, and so this is because it is cos square theta plus sin square theta, right? Okay, and what happens to the inner product? The inner product, when you apply this formula, you see that the first term is there, and the second term you will have the complex conjugate, so j becomes minus j. So now what happens, you can take the common terms, and only thing which is different is L1 and L2. So you have L1 minus L2. Okay, so now you can integrate, right? E power some function here, you are having some constant you are having here, e power some alpha times of t, so that alpha will come in the denominator, right? So you have integral 0 to t e power alpha t dt. So what is the integral of this? E power alpha t by alpha 0 to t, right? So here exactly the same thing we have done. Only thing here, alpha is j 2 pi L1 minus L2 by t. So exactly this is there in the denominator, and when it comes to the numerator, you have to take the reciprocal of it. Okay, so now you have taken this term, and then you are applying the limit 0 to t. So you have applied t and then 0. So you see that you can apply this formula here, and you can see that the first term is 1 and the second term is 0. So you get e power j 2 pi L1 minus L2 is just 1. So this is 1 and this is 1. So 1 minus 1 is 0. Okay, so what is that we see? Norm of these vectors are all square root of t, and their inner product is 0. So it means what? Again we are having an orthogonal set. Okay, when L1 is not equal to L2, so it means they are orthogonal here. So this means they are orthogonal. Okay, to make it orthonormal, now what is the next step? You simply divide each of this by square root of t, right? Then you will get an orthonormal basis. So again you do the exact same procedure, which is projecting x of t onto this space, and you apply the same exact method here. Okay, and then now what we are doing, so the exact same thing here, you see 1 by root t, 1 by root t is 1 by t, and then remaining inner product x comma 1, and this is nothing but your c naught, right? So your c naught is 1 by t integral of 0 to 1 x of t dt, right? So that is what you have here. E power 0 becomes 1, so you have for L is equal to 0. Same way you can check it for any L. L is equal to any integer you take, and then you can see that you will get these as the coefficients. Okay, so here if x of t is real, then the exponential form can be simply reduced to the sinusoidal form. Okay, how to do that, I'll show you how we can do that maybe in the upcoming exercise. So what have we seen in this complex signal? So for complex signal, what are the orthogonal vectors we are considering? The vectors we are considering are e power j 2 pi lt by t. Okay, so here we have normalized them, and we have got this set of vectors here, and this forms an orthonormal basis. Okay, fine, and this x of t will converge to this x of t, the complex signal x of t. Okay, fine. Now let us see for a real signal, how can we find the relation between the sinusoidal form and the exponential form. Okay, so for real signal we have seen only the sinusoidal form. How can we check whether it is related to the exponential form or not? Yeah. So first of all, here let us take xk of, so let's look at the term xk of t. What is our xk of t? C naught plus c1 e power j 2 pi 2 t by t and so on, right? So let's write this first of all. Okay. So c naught plus c1 e power j 2 pi t by t plus etc. ck e power j 2 pi k t by t. So we have written up to this part where you have the positive integers, right? And then let's write the non-negative integer part as well. So which is plus c minus 1 e power minus j 2 pi t by t plus and so on c minus k e power minus j 2 pi k t by t. All right. So here you see that you have c. What are your cl's? This is your cl, right? This is your cl. Now what is c of minus l? What is c of minus l? If you apply in the same formula, where you will have change, can you tell? Instead of l, if I am putting minus l, what will happen? Instead of l, I am simply replacing l with minus l in this expression. So what will I get? I'm not asking anything complex, just exact term what you will get. That's all I'm asking. No simplification, nothing. When you apply L minus L, yeah, the power becomes positive, right? So here you see that you have 1 by t integral 0 to t x of t e power j 2 pi L t by t dt. Okay, so this is your c minus l. Okay, now we are having a real function x of t. Okay, so now note that, so now note we have taken x of t to be real. So if x of t is real, what happens to cl bar? What happens to cl bar? In the cl bar, this part will remain as it is because it is just a real function, right? Only this part you will have a change. So now when you take the conjugate of this, then you will get actually 1 by t integral 0 to t x of t e power, when you take conjugate, what happens to e power I theta when you take conjugate? What is conjugate of e power I theta? Yeah.
minus
Yeah, e power minus I theta. So now you have minus I theta here, so that becomes plus. So you have e power j 2 pi l t by t dt. So now this is only when x of t is real, right? So now you have this expression and you can see that it is exactly same as c minus l. So cl bar is same as c minus l. Okay, so this you have observed. You please hold on for a minute. Yeah, sorry for the interruption. Okay, where were we? Yeah. So now we have seen xcl bar is same as c minus l when x of t is real. Okay. So now how can we apply it here? Okay. So what is that we can note is that. So let us now look at these coefficients here. So here you have, let us just take one particular coefficient and see what's happening. Okay. So C CL, what is this term? E power j 2 pi LT by 2, right? So T by E power j 2 pi LT by T. I have just taken one term here, and let's take one term here and see how can we combine it. C minus L e power minus j 2 pi L T by T. Okay, so I have just taken a pair of these two, and let's expand. So CL, this is cos 2 pi L T by T, and here plus j sine 2 pi L T by T. Okay, and this plus C minus L cos 2 pi L T by T, and here since minus is there, you have minus j sine 2 pi L T by T. Okay, now let's see how to obtain whatever we have, the relation we have obtained here. What is the relation we have obtained? CL bar is same as C of minus L. So how can we use this? How can we use this? So here you have cos 2 pi lt, this term is common. So, and you see that instead of cl you can put cl bar, so you can write cl plus cl bar times cos 2 pi lt by t plus j times cl minus cl bar, right? Cl minus cl bar sine 2 pi lt by t. Okay, now what is z plus z bar? When you take any complex number, when you take any complex number, what is z plus z bar?
2 times real.
It is real part of 2 times of real part of z, right? It is 2 times of real part of z, right? And what is z minus z bar? Z minus z bar is, so x plus, you take x plus iy minus x minus plus iy, right? You have a bar here, so you will get 2 times of imaginary part, 2 I times of imaginary part of z, right? So the exact same thing we are going to apply here. So if you apply that, then you will get 2 times of real part of cl into cos 2 pi l t by t, and here you already have a j, and apart from that cl minus cl bar is 2j times of imaginary part of cl into sine 2 pi l t by t. Okay, so now you can rewrite this. So this is the same, this expression is the same, only here you have a simplification. This becomes minus 2 times of imaginary part of cl into sine 2 pi l t by t. Okay, so now you know that one pair how it has become, you can see, right? So like this you can replace each pair with a sinusoidal term. So you can see that now the entire exponential term you are able to express it as sinusoidal form when x of t is real. So is this computation part clear to everyone? What have we done here? Is it clear to everyone? Yeah, just some simple computation only. So we are just seeing how this expression will turn into sinusoidal form when x of t is real. Okay, is that fine for everyone? Yeah. Okay, so the next part here is that find the exponential Fourier series for x of t, which is given by this. I have already given you the hint. From this, you are going to write the exponential. This is just a one line answer. Okay, you are simply going to substitute the formula here. Okay, and write it in terms of the exponential form. That's all. Okay, the simplification that you can do. But what is the first step? Can you tell? Apply this formula and tell me what is the first step. X of t is equal to, apply the first formula. How can you write x of t?
Converting the sine 2 pi t in the with the exponential form. That's
Yeah,
what. Sine 2 pi t is 1 by 2j e power j pi t
e power
2
j
2 pi t.
2 pi t, right? Minus e power minus j 2 pi t, right? This is the expression for sine 2 pi t, right? This is the expression for sine 2 pi t. Now you have to do the same for the next term. So for the next term cos 4 pi t, you have to write 1 by 2 e power j. Now omega is 4 pi. 4 pi t plus e power minus j 4 pi t, right? And again, so you have sine 8 pi t, so you have 1 by 2 j e power j 8 pi t minus e power minus j 8 pi t. Okay, so you see that this corresponds to cos 4 pi t, and this corresponds to sine 8 pi t. Okay, we have just applied these two formula. Okay, so in Fourier series, the only thing you need to remember is this particular form for real functions. For real functions, you need to remember this xk of t and this coefficients. Depending on the interval, you have to do it as 0 to 1 or 0 to t or the corresponding intervals. This is the exact formula for Fourier series for real signals. And for complex signals, the thing you have to remember is this, only this part. So you only have exactly these functions, right? E power j 2 pi lt by t, only this part, and L varies over integers. Complex actually is much easier to remember because you have only one term, e power j 2 pi lt by t. Okay, and then you know that, so you are just expanding L over all the integers and you get these expression here. So this is the expression you are having for the complex signal. Okay, and then some basic things about this complex numbers you should know to answer some questions like this. So e power I theta, when you take the complex conjugate, what you are getting, and what is the sine and cosine formula in terms of exponential. Okay, so some very basic things, if you know, you should be able to answer topics from Fourier series. Okay, so for Fourier series, I have told you what are the main things you need. Okay, so that should be sufficient for you to answer questions from Fourier series. Okay, so week 11 topics are very less compared to the other topics. So with this, week 11 gets over. Okay, so in today's session, are there any questions? See, this is something very new for you, so it may be vague, but the basic thing is that what is the projection formula? First of all, the projection formula, if you know that, you will be able to understand the very first thing which we have done. How did we obtain this? That is because we have applied the projection of this onto this. Now, how can we apply? What is the projection formula of one vector onto a subspace? This is the first thing you need to remember. So those who feel that this is very vague, check this formula and compare it. You will be able to understand it much better. Projection of a vector onto a subspace. Go back and look at this topic. Okay. So go back and look at this topic, write down the formula and then compare it with what is done here. You can see that exactly that formula only is applied here. Okay. So once you can see that it is the projection formula, then this whatever written is just simplification. And the other thing you need to know is that what is the L2, capital L2 norm. So in capital L2, how inner product is defined, how norm is defined, that you should know. So if you know these two things, you will be able to understand it clearly. Okay. So that's all in week 11. So the next session is on Tuesday, where we will be revising topics from week 1 to week 4. In week 1 to week 4, if you have any specific doubts, you can let me know, so that during the revision session we can discuss those specific topics in detail. So maybe you can put them in the G chat. Okay. If you have any specific doubts from week 1 to week 4. Okay, because at the moment, if you are trying to explain me the question and then I'm trying to understand the question, it is going to take time. So if you can tell me in advance, we can do it quickly. Okay, fine. So we will meet again on Tuesday for revision session. If you don't have any questions, shall we wind up?
So
Yeah.
for the exam, the last 3 weeks, right? 3 weeks will be a lot of questions, and for rest of the weeks from 1 to 8.
1 to 8. Yeah. So 1 to 8 you can consider as like approximately 50%, and the remaining is approximately 50%. Yeah. So more weightage for 9 to 11. Okay. Fine. So see you all. Thank you.